Hey guys, this is the AP Calculus video lesson on FTC Part 2. So remember, FTC Part 1 is really just like directions on how to take a definite integral, right? So FTC Part 2 is more about the relationship between derivatives and integrals. So it should make sense to you that derivatives and integrals are basically like opposites of each other. You can think of them as like inverses, right? Like, so if you differentiate something and then you integrate it, you get the original thing that you started with, right? And vice versa. If you integrate something and then you differentiate it, you get the original thing that you started with. So that's essentially what FTC Part 2 is saying. Here's what it says in more formal terms. It's saying that the derivative of the integral from a to x of f of t dt equals f of x. Okay, that's what the fundamental theorem of calculus says. And in this expression, this could be any number. And this variable, that's the variable x. And it has to match with this variable. Okay, that's the whole deal. And if you think about why this is true, it kind of makes sense. Like, suppose capital F of x is an antiderivative of little f of x. All right, suppose that's true, right? Then what we really have up here, if you look at just the integral part of it, this is really the derivative of, using FTC Part 1, this definite integral is just going to be capital F of x minus capital F of a, right? But we know that if we're differentiating a difference like this, you can just differentiate the first term and differentiate the second term, right? So the derivative of capital F of x, well, if capital F of x is an antiderivative of f of x, then the derivative of capital F is little f, right? So this is just going to be little f of x minus the derivative of capital F of a, but that's just a constant, right? A is a number. So when you take an antiderivative and you plug a number into it, you get a number. This is 0. So it makes sense that what this is saying is true. The derivative of an expression like this equals f of x. Okay, so problems that involve FTC Part 2 are super easy. Like, they'll give you something like, they'll say, find the derivative of the integral from -5 to x. And then they'll give you some crazy complicated thing here. Like, for example, they'll give you something like inverse tangent of e to the t squared dt. It doesn't matter how complicated this integrand is. All you're going to do is you're just going to take x and substitute it in for t. That's the answer. So the answer here would be inverse tangent of e to the x squared. Done. That's the answer. Okay, super easy. Now, there are some variations. There's a chain rule version of FTC Part 2 that says if you take the derivative of the integral from a to u f of t dt. So in this case, see that. So in this case, the u is a function of x. Well, let's think about what this would be before I just tell you, okay? If you look at the integral part of this, this is like capital F of u minus capital F of a, right? If you take the derivative of that, what do you get? You have to differentiate capital F of u, which would be little f of u times u prime by the chain rule, right? The derivative of f of a is still 0, right? So the completion of the chain rule version of FTC part 2 is really just, this is going to be f of u times u prime. That's it. So if it was something like, for example, find the derivative of the integral from 7 to sine x of 2 to the t plus 5 dt. The answer would just be 2 to the sine x plus 5 times cosine x. I just took sine x, substituted it in for t, and then in the end I did the chain rule. I multiplied by the derivative of the u, which is the derivative of sine x. And that's it. That's the answer. Okay. Sometimes you might have an FTC problem where there's a variable on both the top and the bottom of the integral. So for example, ddx of the integral from u to v f of t dt. In this case, both u and v are functions of x. Okay? I mean, I could go through the same analysis that I just did. I could say this integral part is really just going to be f of v minus f of u. Well, what's the derivative of that? The derivative of that would be little f of v times v prime minus little f of u times u prime. And that's it. That's what this is. This is just going to be f of v times v prime minus f of u times u prime. All right, so those are the 3 different types of problems that you'll see for FTC. So in this case, if it was like something like the derivative of the integral from x squared to 3x of something like cotangent t dt, the answer would just be cotangent 3x times 3 minus cotangent x squared times 2x. Okay. Now, another way that this is used sometimes, FTC part 2, is sometimes they'll give you an integral defined function. So here's an example. This is actually borrowed from an actual AP question. This is just, it's not exactly the question that was on the AP exam, but it's a variation of it. Okay, so suppose you have this graph, f of x, okay? It's a piecewise linear function. And suppose we have another function, g of x, which is just defined to be the integral from 2 to x, okay, of this function, f of t, okay? Well, the first thing that you should realize in this case is that if I were to take g prime of x, which is the derivative of this, I get f of x. So this function that they're giving us is actually prime of x. Okay? Just that understanding alone is enough to answer a lot of questions in this case. Like, in these first series of questions where I'm asked to find g of 8, g of 2, g of 0, I just use the simple definite integral. That's it. So like g of 8, this would just be the integral from 2 to 8 of f of t dt. So I have to use areas, right? Like if I look at the areas here from 2 to 8, well, 8 is like here, right? So the area from 2 to 8 would be this triangle, right? Which I could just think of it as like two triangles like that, and then there's one right here. So this is positive, this is positive, this is negative, right? So really the total area, if you look at the signed area, would just be the area of this first little triangle. 1/2 base times height. 1/2 of 8, that's 4. The answer would be 4. If I'm finding g of 2, g of 2 would be the integral from 2 to 2, f of t dt. And you should know definitely by now that's 0, right? Because the limits of integration are equal. How about if I'm trying to find the integral from 2 to 0, right? I'm just plugging in 0 for x up here. That's all I'm doing, right? This would be f of t dt. The limits of integration are switched, right? Usually you would go from 0 to 2. So if I go from 2 to 0, I'm going to get the negative of the signed area from 0 to 2. So from 0 to 2, that's 4 as well, right? So this would just be negative 4. Okay. Now, if I'm asked to find g prime at certain numbers, like g prime of 4, this is g prime. So g prime of 4 is just what the y value is at that point right there. The answer would be 4. G prime of 6, 6 is here. G prime of 6 would be the actual y value at that point. It would be 0. That makes sense? If I'm trying to find g prime of anything, it's just what the y value on this graph is. You're not looking at where the points are and the slopes of this. That's for the third part of this question where you're trying to find g double prime. G double prime is really the derivative of the graph that I have here. Okay, so if I'm trying to find the derivative of this graph at 3, well, 3 is here. The derivative of that graph would be the slope of that little line segment right there. The slope of that line segment is 2, so this would be 2. G prime of 0, look at my graph. This is, or g double prime. This point right there has no slope, right? It's undefined slope because it's a corner, right? The derivative is not defined at that point. So if I'm asked to find g double prime of 0, that's the derivative of this graph. The derivative of this graph at 0 would be undefined or does not exist or whatever. Okay? So once you're able to make that connection, that if they give you an integral defined function like this, that its derivative is really the function that you have, then you can answer all sorts of questions. I could have answered questions about mins and maxes of G because I know what G prime is. It's this graph right here. I could answer questions about inflection points or concavity because I know that the derivative of this is really G double prime. Okay, so once you make that connection, this connection right here is the most important part of this problem. Just understanding that connection. Okay, and that's really just FTC part 2. All right, that's it. Remember, there's no lesson tomorrow, and there's a handout in Google Classroom for you to do that relates to more just FTC type problems. So you should have 3 Google Classroom assignments to do this week. One of them is just called FTC and function values. One of them is called more FTC, and the other one's called FTC part 2. All right. So good luck. Let me know if you have any questions, and I'll see you Tuesday, hopefully. All right. Bye, guys.